Let's get started. Last class. You made it. Yeah. Okay. So we'll be finishing off geometric optics today. Lenses and mirrors. And let's see. A few other things. Oh, there is a help session tonight, 7 to 9 p.m. I'll post the room on Moodle. But yeah, 7 to 9 p.m. Most of you showed up for the conceptual test last night. Those of you who didn't and haven't yet made arrangements with me, I have an office hour today from 3 to 4 p.m. Show up to that and you can take it then. Okay, so optics. All right. So over the course of the semester, there were a variety of questions where I said, oh, okay, I'll get back to you. I intend to do so. So, well, some of them are already up on Moodle. On Moodle, you can already find an explanation about why the sky of Mars is red, and also about the history of how they measure the speed of light. So those two links are up there. We also had a question about the fisheye lens. So this, I freely admit, my knowledge is pretty much from Google and Wiki. But basically, the idea is that you have a large diverging lens and then a converging lens. So I think maybe Samuel had guessed that it was a combination. And so the idea being that, okay, yeah, you get these rays coming in from all directions. And if it was, let's see, so the natural tendency is to go like this. If it was a converging lens, it will correct it even further closer to the horizontal. The fact that it's a diverging lens means this is actually not quite that, probably down here. You end up with rays like this. And so, yeah, and then this will, once you get the spacing exactly right, this will converge it at whatever sensor or screen you have. So yeah, fisheye lens is a combination of extreme diverging lens and then some converging lens appropriately placed. All right, so that's fisheye. Let's see, what else? Oh, there was a question about microwave, the experiment with the polarized microwaves, and there's a question about diffraction effects from the grill of bars. So I checked with Dr. Sherry because she's much more knowledgeable about optics than I am. And we agreed in the end that yes, there are diffraction effects, but because the emitter and the receiver were in a straight line, even if you put a grill here, the zeroth order thing is there should be a bright spot in the straight line. And so, I mean, the diffractional effect, will there be bright spots here or here? But in a straight line, the main thing is it being absorbed or not? Let's see, what else? There had been a question from Harry earlier about transformers, where we had, primary coil, and then say secondary coil, and then this was connected to like a light bulb. And in the demo that I had, I could change whether it was a step up or step down transformer. And what we saw was that when it was a step up transformer, and so when the secondary coil had more turns than the primary, then the bulb got brighter. And so there was a question there about, well, we had argued that power in equals power out. So why would it get brighter if it made it a step up or a step down? And so the reason there is that, let's draw a step up one as well. Okay. So the reason there is, it's true that for an ideal transformer, what goes into the primary coil will, power-wise, what power goes into the primary coil will come out of the secondary coil. And we were close enough to ideal that that wasn't the issue. The issue rather is that how much power goes into the primary coil depends upon what is attached to the secondary coil. So it depends on the load is what we say. So just like how a battery gives out different amounts of current or power depending upon the resistors you attach it to, the same way, depending upon what is attached and whether it's a step up or step down transformer, the effective resistance is different. And so how much power comes from the power supply, right? Or rather, this is AC power supply. How much power comes from the power supply changes depending upon what load it is attached to. So that is why we got in the step up transformer case, it turned brighter. And that was also, there was a similar demo we had where I was wrapping wire, sort of creating a transformer on the fly when I was wrapping wire around that core, and the same principle held there. The amount of power was being supplied was changing, and so the light bulb got bright. Okay, and I think there was one more question about the simulation and like what the width of the beam meant, and that turned out to be fairly easy, and I'll show you in a bit. But were there any other questions that I've forgotten and that I promised to get back to people about? No? All right, cool. Okay, so we have all of that. What else? Okay, let me just get some stuff sort of not exactly out of the way, but on the board so that we have it as working details. So we ended last time by saying that we have this equation. This holds for both spherical mirrors and also spherical thin lenses. S here is the object to, let's see, I need a word to denote both mirrors and lenses.
Surface.
Yeah, sure, okay. No, sorry, overruled you. Let's just say optic element, which is a little bit of a mouthful, but there we go. Okay, object to optic element distance. Actually, you know what? Surface would be fine. S prime is optic element to image distance. F is the focal length of the optic element. Okay, we can also talk about magnification. We usually denote by little m. So the basic definition of magnification is it's the height of the image over the height of the object. So it is y prime over y. Okay, so let's put it in brackets, height of image, height of object. And it turns out we can show that the magnification is also going to be equal to minus S prime over S. And I'll sort of argue for this. I won't give a like rigorous proof, but I'll argue for this. So we have this. Wait a moment. Only for mirrors, so all this so far has been true for both, and then only for mirrors we have, oh, spherical mirrors. We have F is equal to R over 2. And then, but then again, for both mirrors and lenses, we have the convention that about the sign of F. So F greater than 0 is for converging lens or mirror. And then F less than 0, negative focal length is for diverging. Yes.
Is F being positive or negative always dependent on which direction the outgoing waves are?
Oh, I see. No, you can take this pretty much. It just depends upon whether it's converging or diverging. So regardless of whether the image is real or virtual, or like which side of the lens the rays go through, if it's a converging lens, you have F positive. If it's a diverging lens or mirror, you have F negative.
So F is positive when it's on the left or the right.
Well, just to be clear, so like say we had a convex mirror, so then F would be negative. It's a diverging mirror. But I mean, it's not particular to necessarily being on the left. I could have a diverging mirror like this, right? That's still a F being behind it. Well, mirrors are one-sided. So if you put it here, it wouldn't do anything. It wouldn't act like a mirror, is what I'm saying. This side is not reflective. Is that yes? No? Right. The way we're treating mirrors is that they only have one reflective surface, and so, like, yeah, it's a
Wait, sorry, so since F denotes length,
yes.
like, we can't say anything about like where it is based on its sign, but like since mirrors only have one side, we know where it is based on that, because it's always gonna be on one certain side of the
For a mirror, yeah, it's always going to be on the reflective. Whoa, the focal length, you mean? Oh, sorry. Okay. My mistake, Alex. I think I got mixed up with the lenses for a moment. So the sign, though, is simply okay. So yes, why do we say that this has a negative focal length? Okay. So there are sort of two ways of talking about it. And then, yeah, let's talk about the sign conventions. Okay, so the sign convention okay, for S prime and for F and R, everything except S, basically, okay? Positive if on same side as outgoing waves. And negative if on opposite side. Of outgoing waves. Okay. Put it out of the way and then sort of illustrate what I mean. Okay, so I'll do it on the first board over there. Oh, question, yes.
Yeah, so if f is less than 0, doesn't that imply that that the image to vertex distance would be greater than the like the absolute value of it would be greater than the object to vertex distance?
I mean, I'd have to work the math, but probably. I mean, you're just talking about rearranging this equation and solving for one, right? Or...
Yeah, like I'm saying if s is positive, but s prime is negative, isn't the only way to get f to be negative if s prime is bigger? Or no,
a smaller, yeah.
Okay. Could you not have a mirror that had it larger?
Well, I mean, you only have the mirror's focal length is determined by its geometry, and then you control the object distance. You don't get to choose where the image is. Yeah. Harry?
I just want to ask the sign convention for M and Y. Like, so for M, just if it's like a plus, does it mean it have the same direction as the?
Yes. Okay. So let me. Okay. Sorry, Alex. I'm going to go back to that board for 1 second. Let me just put up a few rules over here. Okay. So M is positive. So if your magnification positive, it's telling you the image is upright. If your M is negative, your image is inverted. If your magnitude, absolute value of M is less than 1, image is reduced. If absolute value of M is greater than 1, image is magnified. Okay. And finally, if S prime is negative, image is virtual. So, I mean, the ones for magnification are sort of straightforward. If your absolute value of M is greater than 1, then clearly the height of your image is greater than the height of your object, so it's been magnified. If it's less than 1, it's being reduced. And then, yeah, the positive or negative indicates whether are they both pointing up or is like one pointing up, one pointing down. So that tells you whether it's upright or inverted. We'll talk about S prime in a moment. Let me put that there. And now I'll go back to the board. Okay, so let's just do a few examples and see how this sort of plays out. do you want a mirror or a lens first? We'll do both, but like which one first?
Lens.
Lens, okay. Converging or diverging? Diverging, okay. So diverging lens. Every lens has two focal points, and those will always be equal distances from the lens. And so call that F. Call that F. The reason why it has two focal points is one of them is for parallel rays incoming, right? So you can say, okay, rays come in parallel. For diverging lens, they'll then diverge. And those will be in such a way as to appear to come from focal points. Okay, the focal point in this case would be over here. Accordingly. Right, so if you send parallel rays in for diverging lens, they appear to come from this focal point if you look from this side. The other thing is, let's see. The other one is if you aim for the other focal point. Right, so. Right, so you're aiming for this. So you send in light rays along those lines. I'm drawing them back because it's easier to get the straight lines, but yeah. So you're aiming for this point, but then what does the diverging lens do? It will correct those two parallel rays. So just remember it's a diverging lens, and so then you can see that, oh, if it comes in parallel, it has to diverge away from the axis. If it's trying to converge, then it will be diverged into being parallel. William?
So I know you said the side of the focal length, but
Yes.
on the side of the outgoing rays.
Yes.
But if there are focal points on both sides, how does that?
Right. So for lenses, it's partly more of a convention. It's easier to explain for mirrors why that's true. For lenses, it's more of a convention. Yeah. Let me see. Okay, so all right, so that's the sort of general parallel rays setup. Let's look at a specific sort of image case. So diverging lens. And then where do you want it to be? Sure. Let's say the focal point was over here. This is our object. Okay, so I can draw a ray which starts out parallel, and then after it passes through the lens, it's going to diverge away from the optic axis, and in such a way that it appears to come from here. Right, so you get a ray like this. So this is our incoming ray, right? Incoming to the lens. This is our outgoing ray. And we can also draw a ray that passes through the vertex. That will just go through straight. And so again, incoming, outgoing, and we can see that, oh, if you're looking from this side, those appear to meet. Okay, I didn't, hold on, let me correct the slope on this. There we go. Okay. Those appear to meet over here. And so you'd end up with an image over there. Okay, so in this case, you would say, so S is pretty much always going to be positive. I'll tell you about the sign convention for S in a bit, but pretty much all the cases we're going to look at, S is going to be positive. Okay, so S would be positive. S prime, however, the distance of the image from the lens. Oh, sorry, question, yes.
How did you know where to draw the image? I thought it was supposed to come from like an intersection of those rays.
Yes, so I traced back this ray.
Oh, okay.
Yeah. Yes, okay. So, yes, so S prime, we said is the distance of the image from the lens. And here we can see, oh, the outgoing rays on this side, but the image is on this side, right? So that tells us that, okay, S prime will be negative. Questions? Yes.
So it's negative if it's on the same side as the object?
Don't judge it with respect to the object, judge it with respect to the outgoing rays.
Okay.
The reason why I say this is that if you do it with respect to outgoing rays, then you can remember the same rule for both mirrors and lenses. If you do it by the object, then it changes from mirrors to lenses. And so you have more things to keep track of.
It's also negative if it's a virtual.
It is negative. Well, we can see that, yes, it is a virtual image here, and yes, it's negative. And so this sort of explains why we know that it's going to be a virtual image, because the fact that S prime is negative means that the image wasn't on the side of the outgoing rays. So that means the outgoing rays didn't meet, that you had to trace them back in order to form an image, right? Which only happens with a virtual image. And so the fact that S prime is negative tells us that, oh yeah, it's a virtual image. As far as the magnification goes, we can see that Y prime is less than Y. And so our M is going to be less than 1, but still positive. All right, I'll do another example, but any questions about this example? Okay. Let's try converging lens, and then we'll do a mirror after that. Okay, and let's put our object over here. Okay, so one ray starts out parallel and then passes through this focal point because it's a converging lens, right? So it starts out parallel, tries to move it towards the optic axis. And which other ray do you want to do? Okay, sure. Through the vertex. Okay, yeah. Not quite straight, but yes, through the vertex. Actually, do I have a? No, I have a weird curvy stick. I don't have a ruler. Okay. But yeah, through the vertex and meets over here. And so our image would be over here. Right. So what can we say about the various quantities? S is positive. S prime is positive. Yes, it's on the same side as the outgoing rays. And well, F is positive because I told you it's converging lens. This one here, F was negative. We can see the magnification. We can at least see that it is negative. And I think it's going to be like less than -1, so to speak. Oh, the absolute value would be greater than 1, but that's harder to judge. But we can see that it's negative because it's inverted now. So, and it is a real image. Yep, S prime is positive. We've got a real image. All right, any questions about this example? All right, let's do a mirror. So by the way, remember that, well, this is just a convention in some places, but I put the shading on the non-reflective side. All right, so, all right, so center is over here, so then focal point would be here. And let's put our, we'll do a couple of cases. We'll first put our object over here. A question about the, we're good? Okay. All right, so we can do one ray going parallel and then reflecting through the focal point. You know what, we can do another ray going through the focal point and then reflecting parallel. So now our image is over here. So we have S is positive. What about S prime? Also positive, right? Because it's again on the side of the outgoing rays. Right? So S prime also positive. M is going to be negative. Yeah. And we can also see that it's reduced, but anyhow, it's negative is the crucial thing. Now, here we can sort of make sense of the fact that F is positive and that R is positive, right? So the way you would measure R is, would decide the sign of R is look, is the center of the mirror on the same side as the outgoing rays or not, right? So here, yes, it's on the same side as the outgoing rays. And so that tells us that R is positive. And then because F is 1/2 of R, that is also positive. Yes.
There was a question on the flipper. It was some, I don't remember the exact word. It was something along the lines of like, if you were to cover the top half of the object, how would the image look?
Well, is it the top half of the object or the top half of the lens or mirror?
Or the top half of the, yeah,
Okay.
top half of the.
Right. So let's see. What would be a good way to illustrate that? Okay. Oh, okay. Only 10 minutes left. All right. So hurry up a little bit. Basically, what we can say, yeah, this is actually a good way to illustrate. So let me draw one more ray over here. So we know that the ray that passes through this focal point will turn parallel afterward. So we can see that even if I block half the lens, right, that doesn't stop rays from converging and meeting here, right? So that means that you still get to see the full image, but you just get less light reaching there, so it becomes dimmer. There are cases, if you look at a plane mirror and you block half of it, there it is different because now you don't end up seeing the full image. You can only see some of the image. So it's a matter of like, do the rays that reach this point pass through the entire lens, or do they pass through only specific parts of the lens? So here they pass through the entire lens. So blocking some of the lens will only decrease the brightness of the image. But in other cases, you can show that, oh, if you want the rays to reach some particular point, they have to pass through a certain region of the mirror or lens. And so blocking that region will change what the image looks like. Yes, okay, one final mirror example. So convex. So now the center is over here. Focal point is over here. Let me set up the object here. All right, so one comes in parallel, bounces off in such a way that it looks like it comes from the focal point. Another one, let's say, yeah, let's do the vertex, I guess. Not that good. Better. So we have that. Again, these are diverging, but you trace them back and they meet over here. So you get an image over here. And so for this, again, S is positive. S prime is negative. Yep. S prime is negative, and we can see that R is negative and F is negative because now the outgoing rays are on this side, but the center of the sphere is on this side. Yes.
Is there ever a situation where like R, F, and S prime have different signs?
Where R, F, and well, R and F always have the same sign. But you can have S prime be a different sign. So if I move my object here, I would end up with a virtual image, and so S prime would be negative. So yeah, we have, so that's a sign convention for all the various distances. I've mentioned that S is slightly different. I'll just mention it here, but only S is judged by if object is on the same side as the ingoing rays or incoming rays. And S is possible, and otherwise would be negative. Yes, Angelica.
What case, or could you like show an example of where it would be on the opposite side?
Was that the same question you had? Yeah, okay, all right. So yeah, no, that's why I said in pretty much all the cases we're dealing with here, S is always going to be positive. The one way that you could arrange for it is if you have more than one optic element. So what you could do is you could have say lens over here, and so then we know that, okay, this is going to create an image over here. Should use different colors, but yeah, so this would be image one. But then what you do is you can stick maybe yeah, a diverging lens or something over here. Okay, so now obviously these rays will not just pass through the second lens and end up over here. They will do something to the lens, and if you get distances right, they'll form an image somewhere else, right? Where will they form an image? So when analyzing these sort of like multi-stage ones, what you do is you do the first optic element, you find out where the image is, then treat that image as the object for the next one. Okay, and so for this green diverging lens, you can see that, oh, the incoming rays are on this side, but the object for it is on the other side. So that is when your S prime, or your S would be negative. Yes, Angela.
Once you put the second with diverging lens there, though, wouldn't the rays that originally formed that image?
Oh yeah, no, they absolutely will. So they will not meet here, right? But to calculate where they will meet, you treat this as like a new object. Other questions? Okay. Just a few minutes left. Let me mention this. We've done that. We've done that. Oh, the lens maker's equation. Okay. Yeah, I'll mention it at least for completeness. So, what if you don't have a lens? What if you just have rays going from one medium to another? Something. Right, what if you just have rays going from one medium to another? Well, we know about n1 sine theta 1 equals n2 sine theta 2, but that only holds if the surface between them is flat. What if the surface is curved? Right, so yes, there we go. Okay, so for example, supposing you have a curved surface, with some radius r, so this is the center, this is r, and you're going from n1 to n2. How do the rays behave then? So the rule is given by this equation. We have n1 over s plus n2 over s prime equals n2 minus n1 over r. And I don't have enough time to go through an example, but I'll post the slides. The slides are already posted actually on Moodle, so you can see an example there. So this talks about when you're going from one medium to another. What is a lens? A lens is simply two such cases, right? You're going from air to glass and then glass to air, right? And so you can actually sort of do this equation twice. And then in the limit of having a thin lens, you end up with the so-called lens maker's equation. Which basically tells you 1 over f is equal to n minus 1 times 1 over r1 minus 1 over r2. So the idea here, r1 and r2 are, so supposing you had a lens like this and you had light rays coming in like this. So it first meets this surface, right? And so you would say, okay, what is the radius of curvature of that surface? So you would be asking basically like, oh, this is an arc of a circle. And so this would be your R1, right? And you would say that, oh, this R1 would be positive because it's on the same side as the outgoing rays. And then R2 would be related to this surface. And that R2 would be negative because now your center is on the opposite side from the outgoing rays. And n is the refractive index of your glass. So this is the equation that they, well, one of the equations that they would use when basically grinding the lenses of your glasses. Now, I mentioned these are for spherical lenses. If you have astigmatism, you will notice on your prescription, it will say something like cylindrical lens. So astigmatism happens basically when your eye's lens is not curved uniformly in all directions. It's curved more sharply in some directions and less sharply in others. So it's less of a sphere surface and more of a cylindrical type surface. So astigmatism is that sort of error. Yes, Freddie.
Just to be clear, N is the refraction index of the lens.
Yes, of the lens. Yes.
And F is the focal length of it.
Yes, F is the focal length of the lens. Christian.
So in like laser eye surgery.
Yes.
Like shaping the whole lens.
If you're correcting the astigmatism, yep. Other questions? All right. Okay. Didn't plan this out properly. Okay. But I'll end with some demos. And again, sorry for the delays. Okay. Let's start with that one. All right, is that projector on? Oh, it's warm. Okay.
Okay, you're still talking.
Yes, yeah, sorry. Okay, yeah, projectors are warming up. Let that do its. Okay, so nice simple orange on plate, but quite an echo effect from the mirror here. Yeah, what's the light and sound? Oh no, it might be just the microphone on the camera. But yeah, so you can see that. Right, it's a weird thing, and if you actually stand over here, you will see the orange on the plate, but it's actually hidden inside this box and is upside down in fact. Right. So you get, if you stand, you can, at the end of class, just come and stand here, you can see this illusion of an image over there. Finally, with eye defects. Really wanted to spend more time talking about those, but let's see. No, oh, Masi could just log in. Sorry, it locked me at the Mac Mini. Sorry.
You're gonna have to put your stuff in the back room. You have to push stuff in the back.
Okay.
I gotta take off.
That's fine. Oh,
The password is.
no, I think it's just signing in. Or? No, it's not correct. Okay, yeah. Okay, thank you. All right. Okay, so. All right.
There you go.
Thank you. All right. So here we have a camera basically representing our eye. The thing is backward just because of the program settings. Don't worry about that. So you can look at the case where, oops, this one, here we go. You can make it out of focus for near objects. And so let's say it's focused on a distant object over there. Okay, and so you can have, all right, so this is the case where you're farsighted, where you can see far things easily, but not near things. And so in such a case, you would want to correct your eyesight, right, using a converging lens, right? Basically, what's happening is that, okay, things that come from, light rays that come from far objects are almost parallel, and your eye can converge them, okay. But if they're coming from a nearby object, they're diverging quite a lot, and to focus them on your eye the lens needs to be strong, it's not strong enough, so you supplement it with the extra converging lens. And this can happen either because your lens is not strong enough, or because your basically because the focal point of your eye's lens is behind the retina, so your eye might be shorter than normal, and that's why it's focusing at a point behind the retina instead of where it should. We could have the opposite case where you have short-sightedness. You're focused on near things, but then distant things are blurry. And so here the problem is the eye's lens is too strong. And so nearby objects have very diverging rays, your eye can focus those easily. Far objects have nearly parallel rays, and your eye focuses them in front of the retina. And so you want to diverge them a little bit in order to account for that. And there you go. All right, I'll stop there, already way over time. Thank you very much. Hope you had a good semester. Yeah. Hopefully, we'll still see you around on campus or in classes. There is a help session tonight. I think I mentioned 7 to 9 p.m. I'll put the details on Moodle. Yeah. Yes. I don't know yet. Yeah.